natural language processing. And I'm very happy to welcome our first keynote presentation, Isabel Papadimitriou, currently from Harvard University, but about to take up a faculty position at the University of British Columbia. PhD from Stanford in linguistics, who chose the title for her keynote, What Can We Learn from Language Models? And I just feel like reading the first sentence of your abstract. This talk will examine how linguistic theory, many of us, can benefit from the recent surprising successes of language models. Thanks for joining us. Isabel, please, the floor is yours.
Hi. Yeah. Thanks for the introduction. Happy to be here. Thank you very much for the lovely introduction. Yeah, and I'm going to talk about, as I said, what we can learn from language models. So pretty long time, of course, we'll focus on what we can learn about language structure more, given the conference and given just my research in general. And so, yeah, as to find the next stage, the main question I want to talk about is what is the relationship, right, between what we know or trying to find out about language structure and the successes of modern language models, right? So on the one hand, we have human syntax, which helps us generate very many interesting theoretical insights about language, right? It also helps us build solutions for language technology. Again, as implied in the introduction, used to be maybe a very, very large part of, and now it has its pieces in low research language and other more specified parts of the field, right? So there's human syntax on the one hand, right? And artificial language models on the other hand, which are mostly without the use of theories of syntax. And so what's the relationship between them and what science can we do in, as people who care about syntax in this time of language models? And as I'm sure you all know, right, language models learn through self-supervised statistical learning. It's a big pile of language data is usually negative prediction, and you end up with like as I said, naturally pretty surprising linguistic capability, right? Like language models today can handle complex syntax, you want to know your discourse or everything in between or beyond, depending on these ideas, right? And this is a phenomenon that we don't like really understand, I would hazard to say. And this talk is kind of inspecting this phenomenon, looking at how language models kind of end up at and structure their capabilities for like an overall lofty goal of using language models and the research that we use to probe into them as hypothesis generators, right? To kind of expand their abilities in learning and representation. And so what I think is really interesting about language models that in success they fulfill a lot of the connectionist promise or whatever, right? In that they put together aspects from symbolic and statistical NLP, right? Like, so of course, if we take a symbolic approach to analyzing language, right, it actually looks like really beautiful and interesting about abstractions and computationality, but often very symbolic accounts of language, they don't provide kind of details of use and statistics of language use, this matters more or less to different people, right? And on the other hand, right, the statistical approach, right, it has the problems of being able to capture kind of, this like usage first kind of way of thinking about language, but this is what I said is a really interesting part about language, right? Which is like the abstract symbol. And language models, if thought of there in their theory and how they're that's kind of in how they act, right? They combine these two approaches, right? They are statistical models, but they're competent in this symbolic aspect. So the person that, I think we would be pretty hard pressed kind of, get GPT-5 to make some sort of syntactic error, right? Or to have kind of not be able to put a certain line that could go right in the part of a sentence in a sentence, right? And stepping back, to the and empirical aspect of this, right? And then we will start to see two things. I think on the one hand, something I'm very excited about is that they kind of provide me a model in a way that, my sort of animal models or other aspects of cognition, vision and decision making, people have been doing a bunch of intervention is that, language researchers could never do. And they have this empirical test beds, right, for thinking about language learning. This is and this is something which we not really have the chance to do before. An model as analysis for the decision making, language models for human language, but I think it's really useful in pushing science forward. And then on the other hand, that's fully functioning linguistic system, right? We can look inside of like every decision at every stage, right, at every single weight, right? And so we kind of sort of have this functional models around representation, right? How we represent the system in order to do what we do. And so what I'm really going to talk about in this talk is some of this is a few new methodologies for taking advantage of these new areas, right? I think this is what I mostly do in my research, right? It's kind of develop methods for what a language model is doing in a slightly new way and try to think about what that can teach us. And so, kind of go chronologically through the learning process. I'm going to think about, syntax before learning. And so what structures, if we have them in a learner facilitate language research, we're going to think about kind of training dynamics or syntax during learning. So like how our syntax is being built out of this research focus on the comps of the first part of the model. And then, I'm going to do some research looking at, just fully trained models, and the kind of the machine learning providing the roles, right? Which is kind of an abstract thing. And so for the first part of this work I did with my advisor Dan Jurassic at Stanford, during my PhD, and the main question is what do we need in order to learn language, right? So human language learning is statistical, at least in part, it's like the word segmentation, kind of inference studies, right? But what else is there? Without getting very deep into some sort of innateness debate, right? There's what kind of structures make it easier or harder to learn language, right? And the theory is kind of what we've had so recently, right? It's to develop kind of minimal theories that explain a lot about language, and this kind of it would imply that like cognitive bias would be probably good or maybe necessary for learning, right? This is kind of the minimalism approach. But with language models, also statistical, probably more so than humans, we can experiment with the concerning processes, right? We can just switch it out. And so the method here, it's not exactly clear how we do inject structural bias. The method that we went with was injecting structural bias through training. So a non-trained model, this is software. This is not a blank slate. It's some model was structured that's developed over many decades of people trying to do something with neural networks. So it has some sort of bias, some sort of learning bias. It's not easy to know what it is. Same way it's not easy to know learning bias in humans is, but what we could do is that we could train on the formal language, right? And make it just really, really good at modeling some kind of like sufficiently complicated, like sufficiently large vocabulary, such to have two types of bracket, formal language. And then what we have is not bias for bias for modeling certain structures, but not really tiny, and linguistic grounding as seen language. And then we can train on natural language and see how easy the formal languages are. And we experiment between three languages and the first English results that they all pretty small. And the structural skills that they focus on for this talk are recursion, right, which is a very basic idea a very basic structural principle in language, and crossing dependencies. And so something very very basic to language, right? Is that we have these recursive combinable parts, right? So where there's kind of encounter a noun phrase, right? Where we encounter a verb phrase, you can kind of combine them and then we just kind of symbolic recursive principle, right? And but on the other hand, right, this isn't all right. This isn't universally true, right, across all examples in language, right? For example, if I were taking the other noun phrase and the other verb phrase, the sentence doesn't work against because beyond the like parsing the simple kind of syntactic schedule, there's a lot of other relationships that relate, every other word in a sentence, right? That make things make sense, right? From plus, right? Like semantic relationships, and these are often not following these very neat structures. And so we have these ideas, right? Recursion here is again center embeddings, right? And crossing dependencies, right? Is like a naphra that doesn't have to follow the recursive structure at all, right? And we can distill them out to formal language, right? Like a design language with nested dependencies, or a language mentioned dependency that aren't nested, and we can see how well can a language model learn language after it's seen these formal languages, right? And so it's what I'm showing here, right? For flexes in the y-axis or lowers are measured. And what we see is that compared to kind of we have kind of two controls, one where the primary language is like random and no structure, one where it was repetition, so there's kind of maybe just not that much interesting structure as far as we were concerned, or just kind of chunks of like that were just repeated, that's the structure, right? And then both of the kind of more interesting structural principles that we looked at did significantly better. And in fact there was even the starting offered by the crossing dependencies work is even a bit stronger for the language model. Now, what does this mean? Right? Is it a versions for the language or that this is what humans have, right? But what is that kind of this kind of structure? But it's pretty hard to arrive at theoretically, but there's a much more beautiful, like mathematical like that. And so actually show how the empirical root kind of shows us the types of things that might make the language learnable, right? And the kind of relations that can bootstrap other relations, right? And that would be just much harder to arrive at than if we didn't use language models. And so, and so I think what these experiments bring to light, right, is the principal importance of these kind of other structures in language, right, beyond the very coarse syntactic structures that we might usually analyze for scaffolding language learning. And so, I should briefly introduce two more projects that go, one step beyond these results and looking to where these biases might come from, or how they relate to structures in language. And so first we want to ask where do these biases come from, what are their cognitive what are the domains of cognitive processing? Might be relevance and biases, and we're going to focus on music. And then there's a structure in human language, itself somehow better learnable with certain biases, and the vertical algorithms there is not maybe transformers, they have a harder time with impossible language that have kind of unsensible characteristics. And so, so, what influence biases are, right? A question is, where do they come from? Are they just layers somehow built in, or are they a product of statistical structure, or the product of joint learning of like the visual mode as well, or whatever? Right? And our results, so far they don't really take a stand on one over the other. I guess neither of our results going forward, but an interesting question though is, can other cognitive domains beyond formal languages can they accident at the bias, and take inspiration from the generative theory of music, which we all been jacking off at some point. But after we asked, can we just video music act as a different device in the way that some of these formal languages did, and we saw similarly just very strong results from training on video music. So it shows that there's a lot of domains of cognitive processing which kind of have the types of structures that make that make language learnable, or at least more learnable. And so, secondly, I want to maybe take a look at language itself, right? So how do the structures in language interact with variability and biases? And this is a project actually led by with in collaboration with Richard and Chris. But I want to go into it. I think it's pretty interesting, and I think so the question here is, are possible languages or languages kind of unattested structural characteristics, are they hard to learn even for language models that don't necessarily have whatever biases that we have already built in? And so the main idea here is to train models in corpora that we have models already know to have unattested characteristics, right? And so the question is, can they learn these alternate languages as well as they can learn English? And the answer is no. I'll go over it. But I think the interesting thing that we want to look at, and I think is it's just a really cool question for the field. Is why not? Is it because the transformers are just happen to be very similar to students, or is it something about learnability overall, or however kind of language structure is optimized? And so for example, I'm going to take one result from the paper, which is that we all say this preferred counting rules in terms of learning. And so we're looking at counting based inflection. This is the idea that instead of instead of having an inflection, right, we take a corpus language, kind of we lematize all of the verbs, and then we just add our own little mark. So this is kind of the no-off version of the language. It's very similar to just like English, where there's just like a marker, singular or plural after every verb. And then we also create a version of this language where the marker just goes forwards later. So it's informationally the same, because you just have to get before. But it's kind of a strange type of rule that I don't really see attested. And then we also have a version of this using tokens instead of words, because maybe the language model just thinks better in tokens. And what we see is that, there's sort of effect, but there's just overall just worse learning complexity for these top languages, right? So if we look at the grade line, which is the control, which is just more like English, it's just like consistently lower throughout. And then where we see more of an effect is that the marker, right? So whenever the marker appears, right, and it just has higher surprises, it's less expected, right, for the counting parameters. So the color orange and blue bars here, right? So there's a big difference early between these panels involved word training and the axis and survival. And but there's a significant difference throughout training. Right? This is a harder thing to learn, even though it's information equivalent. And the results from the paper, right? We don't at this point really claim an SS as analyzed as to why, but it's a really interesting question to think about both in terms of language models and in terms of just kind of the nature of human language structure overall. Transformers aren't like humans, many things are different. But some things are the same, right? And one of them is causal attention, right? That is models you can't see the future. It's trivial that we would see these similarities in learning, right? The excessive characteristics are less learnable. But for experiments, they look just for like where do the types of language structures that we might be have? Is it an issue of information and locality, right? That this kind of causal attention as well as the just basic fact of the world that we can't see the future. Do these interact make kind of optimal information locality kind of a better paradigm? Is it conditionality, right? That you have a lot of these types of rules. You don't get the same kind of conditionality that with a more normal grammatic system. Similar things like accessibility. And so to summarize all these results, together, language models are an empirical testbed for language learning. I think it's really exciting for someone to play around, and I would encourage you to do so too. Right, language model experiments, they can show us which inductive biases make language learning is easier, right? And kind of happens hypothesis generators, right? And in this case, it kind of shows it's possible importance of these kind of non-recursive head-to-head connections as an inductive bias. They also show the probability of shows stabilities for how these kind of learn your language interactions come about. And again, we kind of got this hypothesis generator, right? Which we learn cognitive domains and the learnable and what might make language as this generative structure more learnable. Cool. And so I would think we can talk about a project that we did looking at training dynamics. So I was sometimes for during learning, and more specifically in language models. So this is work done with J.A. Prince, who does a computational cognitive neuroscience, computational neuroscience, I don't know and we kind of combine some pretty standard techniques, computational neuroscience, so that to think about the matrix. So the abstract syntactic representation in models, it originates in the lexicon in a way it's maybe not so similar to how we think about abstract syntactic representations in humans, in a local or general, or maybe it's, but when I say it's right, so you have the different words, and out of you put them through the matrix, you get a big pile of vectors, so you get one for each word or one for each token, and then we just put these through the model layers. Nothing else informs the model of what we're doing here, right? There's no kind of external process of this is sentence or something, right? Like all we get is this pile of vectors, right? And then somewhere in there we get possible kind of abstract syntactic representation, right? So this is like it's really not like a strict adherence to the words and rules kind of approach, right? Where there's this kind of abstract grammar that's represented separately, right? There's definitely like grammar of the weights, and lexicon of the embedding matrix, but there's no other process for saying what we're doing, or like what's going on, different from manipulation of these embedding patterns, There's maybe like interesting, or like kind of negative value problems for you, depending on, what you believe strongly about language processing, but it's just how they work. And so I think the lexicon is a pretty interesting part of this model analysis. Right. And what we're going to do in this project is analyze the lexicon over training. So how is information in it built up? And the question and the method that we're going to use relatively short symbolic analysis, as this is like pretty standard in a lot of representational analysis, certainly in neuroscience, and it's about how compared to representational spaces that are quite right. For example, the first metrics versus we want to see if they code things like part of speech. And the idea here, and this came from the problem of having a big pile of brain data, and once it doesn't represent this feature I'm interested in, right? And we just have just a lot of readings, and maybe that maybe instead of kind of dealing with the statistics of each space, we can compare the distance matrices, right? So if we just kind of pairwise distance metric of all these vectors and all these parts of speech, we can have like maybe things right now that's zero distance and the two vectors are smaller, so small distance, and then we could just do this across the whole data set that we have, and just do a approach between just these two matrices. Now they're the same size, right? Because it's just like just embedding, right? It's the number of difference by the number of difference. In this case, for example, in the on the so it's the value is 0 to 0 and same or speaking different by having here what we did is just say if they appear as that part of speech, it needs to be over 5 times for some purpose that we use. And so try to be dead non-perfect. I don't think some things of multiple speech. And so so that's the one method. Even it's not as like a hypothesis driven, I would say, right, where you have some hypothesis about structure, or you have human judgment or some type of information, so you have frequency information. This is like two words are close, that's similar frequency rank and font, they're very different. And then we also take the actual embedding matrix distance matrix. We use Python for these experiments, right? And we take the subset that's represented in our in our humor judgments or whatever, we call out have information on every single term, they go to the subset, and then we run publish. And the other thing that we could do is actually just like the last checkpoint. So we have again all of our checkpoints during training, right? We have the last checkpoint, and the way we use kind of our independence knowledge here is that we can take sort of significant subset, right? So this is like, say, what if we take all the functions, we take all the lexicals, or we take all the frequent versions, all the infrequent. And then we can run a correlation between and compare kind of different subsets and how fast they converge. So these are like the two our same methods that we're going to use, and then we find from what I'm saying is that both syntactic and semantic information organizes very early in training. You know, these are the plots for video, which even from all of that size is they're not even trained very long. You know, they have opinions that are about training, I guess, but you know, I think that almost, for example, is a model with a similar size training much longer. We see the same pattern where the information kind of peaks pretty early on, especially the case of all these syntactic measures, right? So you have part of speech and dictionary tags, so this is, you know, the kind of tags we can get a dictionary. Like translated Scottish. And you know, and we also took all the verbs and verb net and the same kind of 0-1, you know, whether they're both indistinct for that class or not. You know, and this just peaks very early, and interestingly, this kind of doesn't even end up at its highest point, right? So it's just organized very early in training. But an interesting result that we had is that correlation with frequency rate climbs much more steadily. Was the only thing that we could find was that when we just found out immediately, right? So it seems kind of, you know, what is correlation with frequency rate? And these ones are the, you know, the distance matrix that we're comparing to it is that, you know, the fifth most frequent word and the sixth most frequent word have distance 1, you know, and then the fifth most frequent word and the 505th most frequent word is distance 500. And so the correlation is just finding much more steadily. Interestingly, we did this policy analysis where we said, okay, so that what is the kind of like everything pops out, and at the end, where everything pops out. And it seems to be that the distribution policy analysis where you picked out the words that are just most closer, and they were all just rare nouns and they're plural, so it's that it's kind of like, you know, when you have these kind of rare inflection forms and tokenizer, right? It takes a large part of just learning the meaning, it's learning that's they're basically the same meaning, right? And so a lot of the work is kind of done, you know, it looks kind of like syntactic or something, but I would say I'd probably call it more like the work that's being done with semantic, right? When you're using functions and using particular. And just like the very tail end of this of the frequency bands and the tokenizer, you're just getting a lot of your translation is sort of trading. And so going to our convergence result, these all similarly reflect, you know, a similar pattern where both close passwords are converting faster than open passwords, right? So here again, you know, on the right, we have the correlation, and we're saying overall training, how much is a subset of close passwords, you know, like it's that checkpoint, and so we said, you know, of open passwords, like it's checkpoint, when we get faster convergence, and I think interestingly, if we look at the beginning, we see that not only do less words go slower, but they also where they end up, right? It's pretty correlated with the random initialization. So you take that statistical and you correlate with set of the IWPT, you get this kind of non-trivial distance correlation, right? So this is a surprising result, right? The random initialization what role in this final representation of thought? You know, we said it was a class, maybe we might figure it infrequent, you know, it's pretty hard to disentangle, you know, and we see, and we see this as well, right? We see the frequency bands, which is what how it works. And you know, with this kind of blue orange line, with like blue being the most frequent, it's the frequency rank, so no, there's that they're about 100, rather than is the lowest one. Yeah, and we see again that more frequent words converge faster, but it's slower per exposure. So this is the same graph, but we just scaled the x-axis differently for each line, right? So kind of estimating how many times on that project words that will have been seen, and then we actually see that it's much slower, right? That more frequent words are like seen a lot more to reach the position of which they end up. There's kind of interesting tension of, of it seems that you might have something that's kind of anchoring role, right? Like, the most frequent words, but they reach it with a lot more training. And then again, we see this this effect, and it can be more somewhere, and then even the 1,000th most frequent, right, kind of bucket, which is, we're not into very rare words yet, right? These are still very complex and are turning out to be correlated with their natural initialization. Cool. And so, yeah, and so the summary from all this stuff, kind of vocabulary, it's organized early, right? Which is, to me, was surprising. I thought that there'd be a lot of kind of building up of these relationships. That's what the language models were doing. That was kind of making them good overtraining, but it seems that later training is more often used for structural organization of low frequency words. And the next steps, there are efficiencies. So how is this kind of, perhaps the rules part, if we want to think of it like that, how do the model weights use information vocabulary for these capabilities? Because you don't really have the good syntactic capabilities of later trainings. You get them somewhere else, but you're not getting more syntactic information in the vocabulary. And I think the way to disentangle some of the issues that come here is kind of is to do some more advanced methods that will look at the evolution or computational profile of individual words, the groups of words, so that we can run some regressions or something, right, to disentangle which of the features are causing them. Is it is it frequency or is it things like usage? And so that was syntax very good. And lastly, I want to focus on syntax and training models, right? Like I kind of believe this fact that there's actually syntax and training models this and syntax models. And I should go briefly into some of a few years ago, kind of trying to look at this idea of abstraction, right? And and this survey general PhD with Paul and Richard John and she Eli Kim and Chantal and Paul, so I'm not talking about, but I'm putting here. And so the main question is, how do language models represent the natural relation? Subject versus object. Does the representation space count discrete changes? Does the code subtract across languages? Then does it count typological differences? And the way we use here is training a subject object classifier, right? So we get a bunch of data points, from UDP corpus, right? We know whether there's some reductions of the sentence, or the transitions. And then we can train this model and get some, and also use so-called probability states, right? There's like areas of your representation space that are very subjective and areas that are very objective. And the first thing I want to ask is, are there discrete changes in subject, right? So if we put if we put a sentence in the chef, right, and we get the subject object placed in their respective representation space, if we then change something in the object, are we going to get this change, or is it represented, with maybe less characteristics that would lead to this also appearing as the chef being the subject. And what we see, these are terms from the community, here's from IWPT too, but what we see on both cases is that over the layers of the model here on the x-axis, if we get these lines that are average over the sentences, you start off with a lexical bias, right? So this is these are the lines for whether you want to think that a sentence to be would be subject, And I like, so I showed this history. But then by the end, it's like it's surrounded with representation, where the object version is represented as an object, right, on this subject object probability space. And so we see that, captured discrete changes, but we only did in English, right? We just started to swap it, didn't maybe just find kind of a word order dimension and say what's first. That would be very likely, right? And so well, what do you see these classifiers and translating between languages, right? So we take a classifier that we used last time in our language, and then we can test the classifier on different languages and see does it still work. And what we see is like kind of sort of again, it works pretty well. So in this case, the red dots are the training is the same, right? So in this case, that red dot will be training on subject object and we tested on German subject object, right? And the black dots are training tests on different languages, and not all cross-language transfer is good, but the English evaluation is just not one of those out of the water, right? So see that at least for many pairs of languages, there's this kind of abstract representation. This is a subject, and I can just zero shot take the same representation space and cut it the same way with the classifier, and that'll also get a subject in a different language that the classifier training has never seen. And so it's that this is encoded abstractly across languages. The question is now, does it capture technological differences? They're not all languages have the same idea of what a subject is. And so in some sense, this, this lots of one level up in abstraction, right? The notion of subject object is abstract, the notion of like how grammar defines subject object, and that's kind of a bit more complicated thing to try and see in just like a vector space, right? And so how is the subject to relation in different languages? I'm gonna be pretty approximate here, but borrowing some terms from conventional methodological literature, if there's transitive sentences and intransitive sentences, right? And you can kind of split their arguments, and you say like the intransitive subject, or A for agent, or object, and then the transitive subject, which one does it pattern with? And again, pretty approximately, there's like nominative languages like English here. We having grammatically in terms of some pronouns or whatever it might be, and transitive subjects, transitive subjects, right? And then there's urban languages that tend to have objects with intransitive subjects. There are a lot of very complicated systems that do various things between. But the main thing I want to emphasize here is that this is like kind of an abstract feature of the grammar of the language, right? Some way that you would say about a language, not about any one utterance, right? And so the question for the classifier is how are intransitives represented, right? So we have the same classifiers that we've had for this whole project, right? And we have an intransitive sentence, it's an individual object, individual subjects. In this case, you have the English classifier and English representation space. So we're going to go with the subjects, and it does. But the question is, we don't transfer across languages. What if we take a different classifier and ask is in the passive system and looks and yeah, so what I'm thinking classifier on the English representation side, it's gonna reflect not that this is, an English translation, but like if this were best, it would kind of go with object. This is again one level of abstraction up. And so the questions are it's kind of information in the same space, or in the English representation space. what we see is that classifiers can transfer these abstract technological things, graphical or everything. But we have, right, we see kind of a difference in these two peaks, right, between how much they will intransit as objects, right, how much they will intransit as subjects, right, depending on whether these are the splitteratives and active classifiers in museums. Yeah, there are three, right, and the yellow line, the yellow distribution are lower distribution. These are all tested on the same points, right? So these are the classifiers are tested on the most qualified region, and then we still see separation. The question is again, why is it zero? Right? It's just kind of less sure, and one might be that one is not really clear. The other one might be as language model clearly has a bias towards non-native language, right? And this conversation is not fully pushed out. Great, and so we see that you know, maybe there should be a more tenuous check there, but you know, there's kind of capturing of this like abstract idea that like abstractions can be shared between languages, but that there's grammatical differences. And so, you know, why is this project useful? You know, why are we talking about birth for 2025? And yeah, I actually to give an example of this type of methodology to show how language models can provide functional example for how these discrete abstract ideas can manifest in continuous space, right? And there's something interesting here. It's a developing methodologies to inspect and stress and stress test this kind of idea of abstract representation in models. And I think there's a lot to be done here, right? And we need to understand how the representation spaces are one of really big models like. And you know, and I think a larger question that this is, you know, if we can understand how one type of continuous activation space can lead to abstract ideas, you know, I think it can lead, you know, I think it can lead us again to hypotheses about how what kind of biological and neural basis for something like syntax might be. Great, yeah. So to wrap up, yeah, I started by saying that language models led us into like revolutionary things for language science, right? That we can intervene and we can fully throw some sort of language learner. And I think this is great. I think that having models push science forward in a way that is very exciting to have in language science. And so I think it's a really exciting time to be thinking about stuff empirically, as a lot of us do. And you know, when I think about, you know, the kind of biases a learner needs, you know, we language models how about showing you features, you know, kind of different structured biases that can come through, you know, the modalities that are useful, you know, why things are vertical, you know, and why certain structures might even exist in language. Right? You know, if we look over learning, right, and we're in we see how language models can learn, you know, over time, kind of build up from information vocabulary and some. And then when we're just delivering models, I'm interested to see how multiple levels of abstraction can be represented in one continuous space. And so the kind of things I'm thinking about just to wrap up, you know, I think it's important to, you know, to conclude with the fact that, you know, the success of expert prediction, it's very surprising that it's not us this far, you know, it's an amazing empirical opportunity, you know, all this work has been on expert prediction text models, right? But, you know, it's really just not like in a position in any way, right? You have to look the objective, there's the environment, right? The amount of information, everything, right? And so, you know, what inroads could be made in bridging this gap? This was like where a lot of the exciting work and this research is going to be, starting out, I've done some work recently that we're going to present in column, we're thinking about vision learning models and their different objectives, and how the geometry networks, fully soon to not fail. Yeah, and with that, I thank them and everything else I've mentioned here, and I would like to, send some questions.